So for example, let's say the rod is more charged towards the ends. It's got more charge. So that would be one example of a non-uniform rod. So what that would mean is this charge is more here, more here. Now I'm going to start spacing them out. Okay, this one I'm going to pull over here. I'm going to pull this over here. Pull this over here. Okay, so I kept the total charge of the rod. Oops. I kept the total charge of the rod the same. You see what I did? I moved the charges to the right, so they're packed to the right side, and they're packed to the left side. What happened to the electric field? Well, it didn't change too much, but it seemed like it increased, 46, you see. So what happens? This charge, which is close to it, is gonna tend to increase here, even though there's more charge here too, but this one that is close causes an increase in the electric field. Okay, so how would we do the integration for this? This is called non-uniform charge density. Non-uniform. Charge density. So let's do the side of the rod, and then we'll do the middle. So let's say I want to know, this one I'm going to do straight up numerical answer. So let's say I want to know 1 meter away, negative half, 0 to a half 0. Okay, so what kind of function should I do for the lambda? The lambda, in other words, lambda is telling you how much charge there is per included in every little square inch of the square meter, right? Or I should say every little distance x. So the lambda, if it's increasing, it means to the right, there's more charge. You see? So I'm gonna kind of say it could be some constant alpha times absolute value of x. So that would take care of the fact that if the charge is increasing linearly, that means as you go to the right side of the rod, this point has twice the charge density as this point, and then the middle is 0. If this point has twice the charge density, it's got twice the more charge here than here. And then absolute value would mean on the other side is symmetric. So if you go here, this point has twice the charge here. So this can kind of mimic our rod. You see, more charge here, less charge, no, almost no charge here in the center. Then you go like this. Or you could make a function that's like this, alpha x squared. Now that would mean the right side, this has 4 times the charge density as this. You see? And then this one has 4 times the charge density as this. So it depends how you move these charges, whether I didn't move them that much, so mine looks more linear. But if I wanted to, I could move a bunch of these more over here and a bunch of these more over here, and it'd be more square looking. That means this would have 4 times the charge concentration as the middle here, you see. So it just depends how you distribute those charges, you see. So I'm going to assume that mine is more linear. And let's see what answer I get if mine is more linear. So how do I set it up? I do the dE is, I'm going to start it from wherever I have the other one. You see how I had this one? Negative L over 2 to L over 2 K lambda dx over L over 2 plus D minus X squared. So that's still true. You see, this part is still true. So then I'm going to put my numerical values, k and lambda. K is going to come out of the integral. This is going to be negative half to half. And then lambda is going to be alpha absolute value of x, right? Alpha absolute value of x dx over, and then this is going to be a half plus 1 minus x. Right, this one I can't go 0 to 0.5 and double. Remember, it's not symmetric. So then the alpha is some constant that I'm going to have to solve for it. So then I take that out of the integral, k alpha absolute value of x dx over 1.5 minus x squared. Okay, so so then let me go and integrate that. I'm not sure if this program can do absolute value. Let's try. Absolute value of x. Oh, we recognized it. Over 1.5 minus x squared, yeah? Yeah, okay, let's see if it works. If they show the steps, they should do this in 2 integrals, right? First go from negative 0.5 to 0, and then 0 to 0.5. Okay, so then, oh, nice, he did it. Okay, so 0.13221696. Okay. Then the k is the 9 times 10 to the 9th times alpha times that number. Okay, now what's the alpha? How do I find what alpha is? So then I integrate this. And then remember dq is, lambda is dq over dx. Well, before I integrate it, let me just write lambda is dq over dx. And then this is alpha absolute value of x. All right, so then dq is equal to alpha absolute value of x dx. Right, then I'm going to integrate that from negative L over 2, or in this case, I'll just go from negative 0.5 to 0.5. Okay, so in other words, I'm saying to find out what alpha is, I'm saying what constant should alpha be so that if the charge distribution of the rod is increasing linearly this way and linearly that way, what should that constant be so that the total charge of the rod comes out to be 10 nanocoulombs? You see, my goal is to make the total charge of the rod 10 nanocoulombs. So what should that constant be? It's a fudge factor that you have to put here. Then once we find that fudge factor, we put it here and we solve for the electrical field, you see. So then Q is equal to alpha comes out of the integral, and then what's the integral of that? Well, I could just go, in this case, I could go from 0 to 0.5 and double because the distribution of the charge is symmetric. So same charge distribution here as here. So then I could just go 0 to 0.5 and double it. 2 alpha, then it'll be 0 to 0.5 x dx. You see? So I got rid of the absolute value, just wrote it as x dx, and now I'm integrating from 0 to 0.5, and then the negative side, I'm just doubling it. And then what is that? X squared over 2, 0 to 0.5. And then the 2 and the 2 cancels. Okay, then 0.5 squared, right? And then 0 is going to be just 0. So then what is that? 0.5 squared, that's 0.25, right? 0.25 alpha. So that means alpha needs to equal what? In order to make this work so that the total charge of the rod is Q. You see? So alpha needs to be what? Q over 0.25, which will just make it 4Q. So in order to work, the fudge factor needs to be 4 times this charge, right? Q divided by a quarter. Everyone go with me there? Okay, now here comes the moment of truth. I put here 4 for the alpha. I'm putting 4 times the charge of the rod. Oh, okay, I'm replacing this alpha by 4 times the, oh, hold on. I've got this thing to account for too. So the electric field is going to be K, so which is 9 times 10 to the 9th. The alpha, I'm going to replace it by 4 times Q. Right? Alpha is 4Q. And then that integral that came out. So that number. Okay. That's going to be the electrical field 1 meter away to the right of that rod. Okay, here we go. Okay, 0.13221696 times, okay, the 10 to the minus 9 will cancel. So times 40 times 9. $47.6, okay. Is that what I'm getting? Not quite. Well, maybe then my equation is not linear. To make it linear, I need twice the charge here as halfway to the end. So maybe go like that, go like that, go like that, go like that. And then here. Oh, now it's good. Oh, yeah. And then there's no charge in the middle, right? Okay, that's a little bit better. Okay, so 47, but I'm in the ballpark. It is bigger than when it was linear. When it was linear, what was it? 45, right? So, sorry, I meant when it was uniform, it was 45. So it is bigger. So yeah, I'm in the ballpark. I'm getting 47.6. Okay. If it was square function, what would that mean? That means it's even more packed towards the end. And then more packed on the left side. something like that. Now it's 48.8. So that's kind of mimicking a square function. It's increasing rapidly this way, 48.8. So you see it's increasing more. So how would you do the square function? What would change? What would change for the square function? This integral will just be k alpha x squared, right? So then we would go to Wolfram this one I don't need to put absolute value because x squared is always positive. Okay, so now the integral came out 0.04555. So it came out smaller. Okay, 0.0, I'll put that in my calculator. 4.555, 845, 832. But then what happens? Can I use the same fudge factor? If you go over here, 2 alpha, no, right? Because alpha needs to be now a different constant because this is x squared. 2 alpha x squared. 0 to 0.5. So you can still double it, 0 to 0.5 x squared. So now the integral of that is x cubed over 3. Oh yeah, no, so it's completely different now. So what that has to happen, q has to be 2 alpha x cubed over 3, 0 to 0.5. And then 2/3 alpha 0.5 cubed. And then alpha is equal to 3q over 2 times 0.5 cubed. What is that? Well, you know what? I'll just put it like that over here. So then I'll have what? Electric field will be, it'll be the k alpha 9 times 10 to the 9th. And then the alpha is going to be 3 times q over 2 times 0.5 cubed.
Wait, Professor, wouldn't alpha just be 12?
Excuse me?
Alpha,
12.
yeah, would it be 12 cube?
Yeah, I haven't cubed 0.5 yet, but maybe, yeah, 1/2, 1/8. Yeah, you're right. So it's, if it's easy, might as well just do it. 1/2 cubed, so that'll be 1/8. And then there'll be 1/4. So then there'll be 12q. Oh, okay, then alpha is 12q. Okay, so even better. So then this is k alpha. So then I have k alpha is 12 times q times that integral that it gave me, the new integral. Okay, so now, so the integral I already put down in my calculator, and then times 120 times 9. Oh, there you go. So it's slightly bigger, 49.2. Okay, let's see. Yeah, it's pretty good. 48.8, 49.2. That's pretty good. right? So in other words, more charge here, you're distributing the charge, more charge closer to the point. But it is kind of weird because also some of the charge is far from that point, you see? So at first, it's not that obvious that the electric field should be stronger. Some of the charge is close, some of the charge is far, but the close makes up for the farness. Okay, then when we come back from our break, we'll do the electrical field in the middle. See how does that change.